Hello everyone. In this talk, we will be presenting DIANE, which is a fuzzing technique for IoT devices that works by identifying fuzzing triggers in companion apps. So this is a joint work from researchers from University of California, Santa Barbara, University of Twente, and Purdue University. I'm Arvind Mechuri. I'll be presenting our work. So IoT devices are inherently hard to fuzz using traditional methods. For instance, using gray box techniques is hard because it requires access to the fuzzer programs, which is hard for IoT devices because they are usually closed source and it's hard to get firmware from these devices. Similarly, black box techniques such as network fuzzers, although they help in generating data to these IoT devices, but they fail to generate data in the format expected by these devices. And finally, emulation of the firmware of these IoT devices is still an open problem. However, a recently proposed idea, IoT Fuzzer, makes a novel observation that most of these IoT devices come with a companion app that helps in communicating with these devices. Okay, so these companion apps usually have a UI that is exposed to users. When users use this UI to modify certain attributes of the IoT device or to control the IoT device, and these UI actions gets translated to messages which IoT, which the companion apps packs into the format as expected by the IoT device, and then eventually the message in this required format will be sent to the IoT device. So based on this observation, IoT Fuzzer finds UI elements that generate network traffic, and then it finds the functions that retrieve data from these UI elements. Finally, these identified functions will be fuzzed by modifying the arguments that these functions accept. So we call this method UI level fuzzing, where the fuzzing is driven by identifying methods that take data directly from the UI elements. But if we look at companion apps usually have two phases. The first phase is input sanitization, where they sanitize all the inputs that app user interface provides in order to drop any invalid inputs. And finally, all the valid inputs will be packed into the format expected by the IoT device by the network serialization component. UI level fuzzing tries to fuzz the IoT device by hooking at the beginning of the app, by hooking at the layer which directly consumes the data from the UI elements. And the network fuzzing works at the other extreme, where it directly sends data to the IoT device. But what we want is to fuzz at the sweet spot, because UI level fuzzing, although it generates well formatted input, it is limited by the input sanitization within the app's code. On the other hand, network level fuzzing, although it has no constraints on the input that is provided to the IoT device, but it fails to generate data in the required format. Ideally, what we want is an ability to generate data in the required format. At the same time, we should not be limited by the sanitization routines in the companion apps. This is the basic idea of DIANE. Let's see how DIANE works. So DIANE uses bottom-up approach. It has four phases. In the first phase, we find the functions that send messages to these IoT devices. We call these methods send message methods. And then we find the functions that transform the data accepted by these send message functions. We call these methods data transforming methods. And then the dominator of these data transforming methods, we call them fuzzing triggers, which will be fuzzed and which enables us to generate properly formatted data on the same, and also input that is not constrained. Let's see how each of our phases work. The first phase is identifying send message functions. Our method is based on two intuitions. Send message functions are usually border functions that sit between the app's code and they interact with Java framework methods. For instance, the code shown on the slide is a border function because it directly interacts with the output stream.write, which is a method in Java IO package. And another intuition is that these send message functions, when invoked, usually generate network traffic. Based on these two intuitions, we develop a method using a combination of static and dynamic analysis. First, given a companion app, we use static analysis to identify all the border functions. Basically, these are the functions that invoke JNI or Android network related functions. Once these functions are identified, we mark them as send message candidates. And then we dynamically hook each of these send message candidates. We let the user use the app to communicate with the IoT device. And then for each of these send message candidates, we record the time delta between the app invocation and the time at which a network message is sent. Okay? And we repeat this for 10 times for each of these send message candidates. Then we compute the mean, standard deviation, and mode for each of our measurements. Finally, we use k-means clustering to cluster these methods based on the mean that we computed. And at the end, we take the cluster that has the minimum mean, and all the functions within that cluster will be considered as send message functions. And the next phase is identifying data transforming functions. Here, to remind, these are the functions that transform user data in the format accepted by the IoT device. And an observation of these data transforming functions is that these data transforming functions usually increase the entropy of the data because they do pack the input data. So they necessarily increase the entropy of the data. So to identify these functions, starting from the send message functions that we identified before, we perform backward slice up to the UI layer of the application. And we identify all the functions that are traversed within this backward slice. And then we dynamically hook all the functions within this backward slice, and we calculate the Shannon entropy introduced by each of these methods. And the methods which introduce entropy is more than certain threshold, we consider those methods as our data transforming functions. For our experiments, we use the threshold to be 2. The next phase is identifying fuzzing triggers. So here, for each of the data transforming functions that we identified, we compute the dominance tree, which includes only the functions which are in the data, which are considered as data transforming. And then the root of each dominance tree will be considered as a fuzzing trigger. So here in this case, there are 2 dominance trees, and the root of the dominance trees is D1 and D3, which will be considered as fuzzing triggers. As an example, let's here set device name is the UI level function, and then send to device is a send message function. And C is the data accepted by the send to device function, which is a send message function. First, we perform backward slicing, which helps us identify all the functions within the backward slice. And then we calculate entropy introduced by each of these functions. And we filter out the functions which doesn't introduce enough entropy. And we only identify, or we only consider those functions where the introduced entropy is more than the threshold. Here in our case, encode is such a function. So we have only one data transforming function, encode, and eventually, since there are no other data transforming functions, encode function becomes our fuzzing trigger. So this is how fuzzing triggers are identified, by identifying data transforming functions. Once fuzzing triggers are identified, we fuzz and monitor for device crashes. So the way we do it is we hook all the fuzzing triggers and run the companion app. So whenever the fuzzing trigger function is invoked, we mutate the set of input variables that are accepted by these fuzzing triggers. We support fuzzing both primitive types, such as int, string, so on and so forth. We also support objects of different classes. However, After fuzzing, identifying whether device crashed or not is known to be a hard problem, especially when the firmware of the device is not available. So to handle this, before starting the fuzzing campaign, we register the amount of traffic generated by each clean run of the app. We also measure the delay bit, that is for that is experienced for each ping message sent to the app. Once we record these numbers, while fuzzing, we monitor the network traffic, and we also measure the delay in device response to ping messages. And we raise an alert if the device generated significantly less traffic, or if there is a significant delay in device response to ping messages. In either of these cases, we consider that device has experienced an alert, mostly device crashed. So to evaluate our approach, we used 11 IoT devices out of 30 most popular Amazon 30 most popular devices on Amazon. We could not find other devices because they were too expensive to be bought. And we evaluated against three evaluation criteria. First is ability of DIANE to find fuzzing triggers. And second is ability of DIANE to find bugs. And finally, the efficiency of DIANE compared to other related work, specifically UI level fuzzing and network level fuzzers. So these are the devices that are used in our evaluation. As you can see, these devices belong to different categories, such as smart cameras, smart locks, smart bulbs, so on and so forth. And as you can see, the fuzzing triggers, and there is the results on the slide shows the efficiency of fuzzing trigger identification. First thing that we can see is that most of these apps, at least 7 out of 11 apps, have at least one sanitization function. This shows that in all these apps or all these IoT devices, the UI level fuzzing will be ineffective because the input will be sanitized by the sanitizer input sanitization phase. And then one thing to note here is in all our techniques, we have no false negatives. So although we have false positives, which is fine, because identifying false positives, we may just spend more time in fuzzing these useless functions, whereas since we do not have false negatives, we never miss a function that is a possible send message or a possible fuzzing triggers. And finally, even identifying fuzzing triggers, we were able to identify with very less false positive, which is almost 10%. And also our effectiveness doesn't depend on the size of these apps, because the size of these apps varied from 4,000 lines to 22,000 lines of code, but the efficiency or the precision of our technique remained the same. And finally, for the vulnerability detection, we were able to find various bugs in different IoT devices, and out of which 3 of these devices had zero-day vulnerabilities. And we were able to efficiently find these bugs where most of the triggers were found, most of the bugs were found within 10 hours of fuzzing. Compared with the related work, which is the UI level fuzzer, the IoT device found only 4 bugs compared to 11 bugs found by our technique. And the network level fuzzers were completely ineffective because most of these IoT devices, they expect data in a very specific format, which the network fuzzers are unable to produce. And we reported all our findings to vendors, and 10 bugs were confirmed and they are being fixed. And one of the bug is still being investigated. Thank you for attending our talk.